Can you see something?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir. All right. So is this not something we'll waste time on? Numbers. When you talk of numbers, we are talking of the number system. In a number system, we have what is called real number system, and we have what is called complex number system. So I hope you know about what the real number system is. So you have numbers. Numbers are divided into two sections. You have real numbers. Then you have complex numbers. From basic school, from the time you start talking, or from the time you were born, you'll be learning about real numbers throughout your life. We have real numbers. You know about rational numbers, right? Do you know about integers?
Yes, sir.
Yes, sir.
You know about integers.
Yes.
What are integers?
They are numbers starting from negative value with negative and positive value.
Negative and positive numbers. So if I have -1/2, could that be called integer?
No, sir.
No, sir.
They are negative and positive whole number.
So they are negative and positive whole number. I thought we treated this in class, didn't we?
Yes, when we did
Yes,
sets.
sir.
Did we?
Yes, we
No.
did.
And why am I going to go over this again? You know what complex numbers are, right? Square root of negative to what? Square root of negative for what is the answer? Hello?
Hello, sir.
Square root of negative for what is the answer?
It is 2.
Positive 2.
Yeah.
Hey, how do you get a positive 2? Richard Apalu. Richard Apalu. Please, you are no blocker, so you can unmute yourself anytime and talk, Richard. Richard, your hand is up. Are you decide not to talk? Yeah, who has an answer to this? I disagree with this gentleman. The answer is not that. Stephen.
Please, it's Stefan.
Stefan.
Yes, please.
Okay, what's the answer?
So the answer will be either positive or negative 2J.
Either positive or negative 2 what?
2J.
D.
With a J operator.
With J operator?
Yes, please.
What is a J operator?
So that's what I'm saying. The answer will either be positive J2 or either negative J2.
Like this? Like that?
No. The answer will be J2. J2 rather.
J2.
Yes, please.
Hey, I've not gotten this understanding.
No, not the capital G. It's the small G.
Small J.
It's like the 2 is multiplying the G.
Like this? Or J2?
No, the first one.
This one?
Yes, please.
No, that's not correct. Yeah. So that's 2I. Okay. So you know how the I comes about? Okay. So are you sure we did numbers, right? Okay, so basically we didn't do numbers. All right, so I got understanding now that we didn't do numbers. All right, so you have integers. Integers are positive and negative counting numbers, right? So you have 0 here, positive and negative whole numbers, 1, 2, 3, up to, they have -1, -2, up to infinity. These are integers. But the moment you introduce fractions, let's say you have half here, the moment you introduce fraction, it's no more integers. Integers are just whole numbers, okay? It could be whole numbers indexed on 0. It could be negative or positive whole numbers. Is that okay? And you know what whole numbers are? Whole numbers are, when we say whole number, we are only referring to positive whole numbers. They are from 0 to infinity. Now, the moment we introduce half, it ceases to be integer, it becomes a bigger body of numbers. So when you have a number, for instance, I'm going to do a top-down approach. So you have numbers here. Under the numbers, we have real numbers. They have complex numbers. Under the real number, we have rational numbers. Tell the gentleman that I decided not to omit anybody.
Evans, you are making noise, Evans.
So we have rational numbers and we have irrational numbers. All right, so I'm going to push Inverse into the waiting room. So Inverse will be sent to the waiting room. So he'll be in the waiting room to make noise. All right. All right, so we have rational numbers and irrational numbers. Rational. So the rational numbers are integers. And integers, I'm just using the word int, okay? And then we have fractions. Fractions. And the fractions could be a terminative fraction or recurring fractions. So that is rational numbers. Then under the integer, you have negative counting numbers and positive numbers, of which we can get prime numbers, odd numbers, and even numbers as well. Then when you count to fraction, we are looking at a terminative fraction. When we say fraction is terminating, a fraction that, let's say, you punch on your calculator, it has a number of decimal points, which is a finite number of decimal points. For example, 1/2 will give you 0.5. 0.5 ends. It doesn't go beyond that. Is that okay? So this becoming a terminative fraction. Another fraction is 1/3. What is 1/3 in decimal, please?
0.3333.
How many threes after the point? Infinity. So you see that you get a non-ending point, decimals. So that's not ending decimal. It's called a recurring because you are seeing a visible pattern repeating itself over and over again. That's 3, 3, 3, 3. I hope that is clear. So all these are part of the rational numbers. Then when you look at irrational numbers, we are looking at a non-terminating and a non-recurring fractions. Those are irrational numbers. For example, square root of 2. What is the value of square root of 2?
The 1.4144213.
It's continuous as long as your calculator space can hold you. So that is, you don't see any part, it's not terminating because it's continuous, okay? It's not terminated. And then again, you realize that there's no specific party repeating itself, so it's not recurring. Is that okay? So square root of prime numbers are all behave like that. I hope that is fine.
Yes, sir.
All right. And you know what prime numbers are?
Let's agree.
Yes.
Let's agree, sir.
Yeah, tell me what prime numbers are as a number, Victor.
Prime numbers, they are numbers that cannot be divided by any number except itself.
Okay. So that's prime numbers. They have only two factors, one at itself. I thought you taught this in class. Oh. Okay. All right, that's fine. So you have prime numbers. Then Victor, please put yourself on mute and as you talk.
Okay, sir.
Thank you. No, it's not Victor. The person under Victor, what's the name? Okay, that's fine. So we are continuing. Now we have, so those are irrational numbers. Now coming to complex numbers, when you punch square root of any negative number, most calculators will tell you math error. Do you agree?
Yes, please.
Yes.
All right. And some calculators, some advanced calculator will tell you keep it real. It's not real. It's not real that exists. And it doesn't mean that does not exist. I hope that is clear. So what happens is it also belongs to a different number domain. So if you change your calculator to a complex number domain, it will definitely give you an answer. But if it's in a real domain, it will tell you it's not undefined, math error does not exist because it does not exist in that domain. Is that okay? So numbers are not only real numbers, we are complex numbers as well. So we're going to do some slight calculation on the real numbers, and then we'll look at some other thing today. So let's look at complex numbers, for instance. Complex numbers are written A plus BI, not J, is B, is I. Okay, so the person who sees J is not J. Now, what this means? A is the real part and I is the imaginary part. What is the coefficient of the imaginary? So if you have, let's say, square root of -4, this is the same as square root of -1 times 4. Do you agree? So this is square root of -1 times square root of 4. So square root of 4, you know, is 2, right? What is the square root of -1? Is I. So square root of -4 is I. So it means that I is equal to it means that -1 is equal to I squared. Is that clear? Hello?
No, sir.
No, sir.
What is not clear? The lady with a sweet voice, that's a no, sir. What is not clear?
The calculation, please.
Well, who am I talking to? Who is that beautiful lady? The lady has sadly forgotten her name.
It's Joanna, please.
Oh, Madam Joanna, my dear Joanna, how are you?
I'm fine, thank you, boss.
All right, thank you. Okay, so I'll go over again.
Thank you.
This is square root of -4. I'm just repeating the square root sign. -4, do you agree that is -1 times 4? Do you agree with that? Joanna?
Yes, sir.
Do you also agree that
Yes,
if I have 4 times, let's say, 16, the answer can be square root of 4 times square root of 16? Do you understand that? Okay, beautiful.
Yes,
so
please.
having understood that, we can move on. So you agree that this is the same as square root of -1 times square root of 4, right?
Yes.
Okay. What is the square root of 4, Joanna?
2.
That's +2, okay? So it's plus or minus 2. Okay. Now, what is the square root of -1? That's what you don't know, right? And I'm saying that
Yes,
square root of
please.
-1, square root of -1 is defined to be a number called I, which is imaginary number. Is that okay? This is a definition
Yes,
you need to keep in your beautiful head, okay? So
Okay.
square root of -1 is equal to I. So square root of -1 here will be equal to what? I. So that's your answer. Do you get it?
So square root of -1 is I, constant.
Yeah, it's constant. It's defined in compressed number domain.
Okay, boss.
Now, how can you put it on the calculator? It gives you 2I.
Okay.
Okay. Do you want to hold that up, right?
Yes, please.
All right, that's fine.
Thank you.
You're welcome. So I'm going to take one example, then we move on. So Joanna, having understood this, I want you to solve this one for me. Yes. Joanna, what is the value of square root of 8 in the simplest form?
Square root of 4.
So this will be square root of 4 times square root of 2, right?
Times square root of 2.
So that will be 2 root 4. Is that
Yes,
2 root 2,
please.
right?
Yes, please.
Okay. Now, what about the square root of -8?
Square root of -8.
Yeah.
Square root of +4
Uh-huh.
times square root of -2.
Uh-huh. That's -1, right?
Yes, please.
So you have square root of +4 is what? 2, right?
2.
Square root of square root of 2 is 2, right? Square root 2.
Yes. Yes.
Then times square root of -1 will be what?
I.
So the answer will be 2I root 2.
Okay.
All right. So the same way, we can do addition and subtraction in complex numbers. But you'll do more of this in discrete mathematics. We are only introducing you that this exists. Is that clear?
Yes, sir.
All right. So there's other of which things are done, board mass, okay? Board mass, whatever you have, any operation you want to do the one in bracket first. Then you do the one off bracket. Like this one is off bracket. Look at D. King, I'm not comfortable you are writing on my screen. Look at this one. The one in the bracket is this one. You do this one first. Once you do, you do the off bracket before any other multiplication, addition, before it's board mass, okay? Board mass. You do the bracket, off bracket, division, multiplication, addition, and subtraction. So please practice all this. They are in your book. Practice them. Most of the programming languages use int for integer.
C++.
It is int for integer, and it is double or float for decimals.
Yes, C++ does.
C++ is double, eh?
Yes, please.
Okay. So integer is int, and then double or float for decimals. So if you see me using it, it's basically talking about the integer. But things like this are called the floats because of the decimals or double. All right. Now the next thing we are going to convert a terminating decimal to that's called irrational decimals, irrational fractions. So converting a terminating decimal to fractions, what we need to do is to, let's take example. First, you have 0.25. We want this to be in a fraction. So what we are going to do is to multiply this by 1. And the 1 could be 10 over 10 is 1, isn't it? Let me look for the guy talking so I can push into waiting room. Who is that talking? Oh, he has muted himself. You agree with him that 10 over 10 is equal to 1, right?
Yes, please.
Yes.
If you multiply anything by 1, the answer is the same one. Isn't the same thing, isn't it? When you multiply anything by 1, the answer is the same thing. Is that correct?
Yes, sir.
Yes.
Sorry,
So,
sir.
and you also agree with me that 10 raised to the power n over 10 raised to the power n is equal to 1.
Yes.
Okay. Now we need to choose the n carefully that all the terminating decimals go to the left hand side of the equal to sign. So look at how many decimal point do you have in 0.25?
2.
2. So our n will be equal to 2. So basically, we are multiplying this over 100 over 100. So 0.25 times 100 over 100, because that's the 2 zeros, okay? Number of decimals. So this will give us 25 over 100. These are not problem because your calculator can easily punch it and it give you the answer. So 25 over 100 will give you 1 over 4, right? So that's how to convert a terminated decimal to fraction. Okay. All right. So another thing we're going to do now, we are going to convert. I hope you are following.
Yes, sir.
Yes, sir. Okay. We are going to convert a recurring decimals to fractions. And the procedure of doing that. You see the number we have here, 0.4, 0.4. This is some dot at the top of it.
Yes.
Joanna?
Yes, sir.
Joanna has gone to the kitchen. All right, the dot at the top of it, indicating that that 4 is continue on ending. Is that okay? It repeats itself on ending. Look at B. Can you see B?
Yes,
Question
sir.
B.
Yes, sir. Yes, sir.
You can see the dot in top of 4 and 2, right?
Yes, sir.
Yes,
It
sir.
means that that set 4 and 2 continue on ending, repeat itself in that pair, in the pairwise manner. Is that okay? So what we'll do is to be able to convert this to a fraction. This one your calculator will approximate to fail you. Because you have this. It's not your calculator that complete it and reversing back. Okay. So what you do here is we need to get to one of the points that are repeating to the left-hand side of the equal to sign. So we have so you let x be the number, the original number that was given to 0.444 this. What I did is the same thing. It means that the 4 is continuously moving. Is that okay? So
Yes.
we want to get to one of these two, the left-hand side of the equal to sign. We want to bring one here. So what do? Multiply both sides by 10. Because it's only one number that is repeating. So you get 10x to be equal to 4.44 recurring. So what do? We are going to subtract. So this will be equation 1, and this is equation 2. So we subtract equation 1 from 2. So you get 9x to be equal to 4. Will be equal to 4. So our s will be equal to 4/9. So that's the answer. I hope that is clear.
No, please.
No, sir, we don't understand.
No, sir.
Who are the
The
weaves?
person was making the noise, so we didn't hear anything. There was a noise at the back, so I wasn't able to hear anything.
The noise is coming from my end, eh?
No, I think somebody has omitted the mic, so there was noise at the back, so I couldn't hear anything.
All right. We need to really get that person in punishing. Bernard, your hand is
Yes,
up.
sir. Yes, it was because of that. Sorry, sir. Let me lower it, sir.
Okay, that's fine. Because you don't understand, that's why your hand was happening.
Yes, I wanted to draw attention. Sorry, sir.
All right. So let me take my time, go through. Okay. The goal we have is to convert the decimal to fractions. So you are giving equation.
Okay. With 20 cedis.
Hey, we just talking about 20 cedis. The 20 cedis part of my work.
1, 2, 3. What is 1, 2, 1, 23. 123. I come out 10 cedis for that.
Who can identify the person talking?
Sir, it's Freeman.
Freeman. So let me put Freeman to a waiting room.
He has muted his mic.
Okay,
now.
that's fine. All right. All right. So the first thing we'll do is to let a variable x to be equal to the number that is given to us. That is 0.4 recurring. Recurring means that 4 continue on ending. Is that okay? So now the sub objective, the next objective is to make sure one of the 4 that is repeating come to the left-hand side of the decimal point. What do? We multiply by 10, right? So this is equation 1. If you multiply equation 1 by 10, what we'll get is we'll get 10x to be equal to 4.4 recurring. Is that clear?
Yes, sir.
At least one person is clear, so I can move on. Right? So this will be equation 2. We want to do away with the recurring point. Is that also clearly understood?
Yes, sir.
Okay. To do away with the recurring point, we are going to subtract equation 1 from equation 2. So equation 2 minus equation 1, what will you have? It means that you have 10x, which is equal to 4.4 recurring minus x, which is also equal to 0.4 recurring. Do you agree? So
Yes.
4 recurring minus 4 recurring will give you 0, right?
Yes.
4 minus 0 will give you 4.
4.
10x minus 1x will give you 9x.
Yes.
All right. So it means that you have 9x to be equal to 4. So your x will be equal to what? 4 over 9.
4 over 9.
So
Okay.
if you put 4 over 9 on the calculator, it should give you 0.44444 anyway. I hope that is clear.
Yes.
Yes, sir.
All right. So because it's only one decimal that is Bernard's hand is up again.
Okay, yes, thank you very much, sir. So if I get to correct one decimal, that is why it is 10.
Exactly.
And an example 2 is 2 decimal point. That's why it is 100. So
exactly.
ask the question: can we assume that, or given that we know that if we always have that, for example, the 0.4 with the dot at the top, can we assume that? It's just a question. Can we assume that then automatically it will be 9x equals to the figure, or we have to state it in a equation form, sir?
On what basis did you assume that? Because mathematics is a procedural programming, okay? Every program you write, start executing step by step, okay? Every program you run have an algorithm it executes through. Is that correct?
Yes,
so,
sir.
Mathematics is underlying factor of the programming that you run. So if you can effectively and efficiently jump to that, it means that you have suppressing some line of codes that possibly are not displayed on the screen. But it doesn't mean that I didn't go through that procedure. Is that clear?
Yes, sir.
All right. So assumption in mathematics are based on the mathematical logics. If your assumption does not follow mathematical logic, then we have a problem. You may get a wrong answer anyway. Now look at this. So first one and the second one is fine. Now look at another example. This second one, because it's two numbers you carry at the same time, that's why you multiply by 100. So you have this. So you let x to be equal to the number that is recurring. We want to get a set of the recurring number before the decimal points. So to do that, we multiply by 100. That's why we have this. 100x. So this will be your equation 1. This will be your equation 2. 100x is equal to that. So you can subtract equation 1 from 2, and you get 99x to be equal to 42. And then you have this. Now, look at the next ones we're going to look at. What do you see in C?
They see it's only two numbers. It's only one number that is recurring.
Yeah. It's one number that is recurring, right?
Yes,
Yes.
please.
But there are two numbers. All right. First and foremost, your original statement should be labeled the X, because that's what you are going to find. Whatever you are looking for should be a mimic of the original statement. Now, one of the number that are not recurring should first come to the left-hand side of the equal of decimal point first, before you do the next move. Now, which number in the decimal here that is not recurring?
2.
2. Okay. So you realize that 2 is not recurring, right?
Yes.
So we first let X to be equal to the original question that is given to you. 0.24 recurring.
Okay.
So we want to get the one that is not recurring to the left-hand side of equal to sign. What do? We multiply by, it's only 1. Is that okay?
Yes.
So we multiply by
10.
10. So we have 10x to be equal to 2.4 recurring. Now the next thing you have, so this is your equation 1. This is equation 2. Okay. Now the rest follow what we did. We are going to get to one of the recurring number to this is times 10 to the left-hand side of the equal to sign. And you realize that the recurring number is only one that is repeating. So we can multiply this by 10. Okay. So we have, meaning 10x times 10 will give us 100x, right?
Yes.
Will be equal to, they have 24.4 recurring. Equation 3. So in this case, we can do equation 3 minus equation 2.
Equation 2.
Okay. So if you do that, you should be getting 90x to be equal to 22.
24.
Why 24?
Yeah, 22.
This will take care of this. These two will reduce this by 2. So that will be 22. So you have 22 over 90 to be your x. Equal to 22 over 90. So the procedure is no different from what is in D. Any question?
No, please.
So can you please go over what you just did?
I should go over what I just did.
Yes, sir.
Okay, I'll go over with another example. Would that be okay?
Yes, sir.
Yes, sir.
Okay. I'll do this. Now, the number given to us is what? We let that one to be what? X.
You know, you know,
0.215. But these two are recurring.
Yeah.
Is that okay? So
Yes,
the
sir.
number that is not recurring will get it to the left-hand side of the point. It's only 1. So we multiply 2 by 10. 10x is equal to 4.15 recurring. Is that okay? Now look at this. So this equation 1 times 10, that gives us that. This equation 2. Now there are 2 numbers recurring. We need to get a set of the 2 numbers to the left-hand side of the equal to sign. So what do we do to equation 2? We need to multiply with what?
Multiply by
100.
100 by 100.
Yes. So if you multiply this by 100, we are getting 1,000 x to be equal to 215.15 recurring. So this is equation 3. So you can subtract equation 2 from equation 3. If you do, the recurring number will go off. We have 213.
Yes.
Which will be equal to
90.
990
990.
x. So you can divide 2 to get x.
Okay.
All right. So can we move on?
Yes, sir.
The next is the modulo.
Sir,
Yeah.
please, is it compulsory that every first question that they give you, the number will start from 0? Maybe 0.1 to 0.34, or you can start with 1.56.
Let me understand your question. You're asking that the problem in life, whether the problem in life will always start with 0.
Yes, please.
Problem does not always start with one thing that you know.
Please.
So it's not compulsory that it will start with 0.
Okay, sir. Thank you.
You're welcome. So you have modulos, okay?
Okay, sir.
Try to read and understand. Then we have number basis. The number basis we'll look at. Okay, I've talked about complex numbers already. What's the time? I think there's some about 7:45.
6:42.
Okay. When we talk of modulo, all that we are saying here is it is an arithmetic of remainder. So remainder theory say that if you divide a number, let's say 5 divided by 2, how many whole numbers will you get in that? How many whole numbers of 2 can you get in 5?
2. 1.
2. So you can get 2 of 2 in 5, and the remainder is what we talk about the modulo. So you write the remainder. It's one of the very key arithmetic. Has a lot of applications in the computer science. You may meet it either this level or elsewhere. I hope that is clear.
Yes, sir.
Okay. So what you need to do is just to take the number, divide by the modulo. The modulo is the division, okay? So The dividend, the number you are dividing is called the dividend, and the number you are dividing by is called the modulo. And the answer you get is remainder. And the remainder is called 2, right? So 22 mod 5 is 22 divided by 5. And we are only interested in the remainder. It will go 4 times remainder 2, isn't it? So the remainder,
Yes, sir.
so the remainder will all be int. The remainder will all be int, int, the integer.
Okay, sir.
So all this talk about that. All right, so these are some of linear combinations you can do. So the next thing, what we'll talk about here now is number basis. You know numbers, right?
Yes, sir.
You know how to count numbers, counting numbers.
Yes, sir.
Okay, which other ladies online, apart from Regina? Is it Regina or Joanna?
Joanna.
Joanna.
Apart from Joanna, which other ladies on the line? On the call. Hey, my dear Ruth, I love to hear your voice. Count 1, 2, 3 for me to hear.
One.
Mm-hmm. Wow.
3.
Wow.
4.
Wow.
200, sir.
200. When you reach 9, after 9, which number follows?
10, sir.
Yeah, how do you write the 10?
1, 0.
So you have 1, 1, 2, 9. Then you write 1, 10, right? 1 remainder 0, right?
Yes.
Then 11 is 1 remainder 1. 12
Yes.
is 1 remainder 2.
Yes.
Out to 1 remainder 19. So the next will be what? 20. 20
Yes.
will be 2 remainder 0, 2 remainder 1, up to so 99. 99. The next is 100, right?
Yes.
10 go to 100 how many times? 10 times, right?
Yes.
And 10 go to 10, 1. So that'll be 1 remainder 0 and 0. And that's how we write 100, right? You know,
Yes.
this kind of thing we are doing, the thinking and the logic behind it is remainder and the dividend, okay? It's a modulus. But because we are counting in base 10, it gets to 10, we write 1, 0. But if you are counting a base like base 12, if you go to 10, you don't write 1, 0. Is that okay? You don't write 1, 0. If you are counting in base 9, let's count in base 3. Base 3, you have 1, 2, the next is 3, right? 3 go to east how many times?
Once.
Remainder
0.
The next is 4. 4 is more than 3. So 3 goes to 4 how many times?
1.
Remainder 1. The next is what? 5. 3 goes into 5 how many times?
1.
1 remainder 2. The next is what?
6.
3 go into 6 how many times? 3 times?
2
So you
times.
have
2
3
times.
remainder 0. But this 3, you cannot get number in a counting number string that will be equal to the base or greater than the base. So these 3 here, 3 goes to 3, 1, remainder 0, and this 0. So you write this in base 3. Is that okay? But because we are born with counting in base 10, decimal base, and we agree with counting in decimal base, and you continue to university with counting in decimal base, that it gets to this level and you get confused. You don't see the algorithm, logical processes behind the numbers. Is that clearly understood? So these are the logical process. So it means that this will be 100, the next will be 101, 102, the next will be 103. But 3 here is equal to the base. So 3 goes here, it will be 0, 1 remainder 0. So this rather 110. Then the next will be 111, 112, the next will be 120, 121, and so on and so forth. Any question?
Sir, can you take it again?
Okay, please take it again first.
What should I take again? The whole show.
From the beginning, please.
So this is, we are counting in numbers that are other than base 10, okay? We are going to count in base 10. When you get to 1, 2, 3, up to 9, the next is 10, right? 10 is the base. Is that okay? So
Yes, sir.
10, how many times does 10 go to itself?
1.
1 remainder 0. And we call this 10, okay? It is only 10 if you are counting base 10. The base will always assume 1, 0. Okay? The next is 11. 11 is what? 10 go to 11 how many times? 1 remainder 1. 10 go to 12 how many times? 1 remainder 2. 1 remainder 3. Up to 1 remainder 9. The next is 20. 10 goes into 20 how many times? 2 remainder 0. Right?
Yes.
Okay. That's how it is. That's the count is this. So it means that we have 10, we have 20, we have the next to be 30, right?
Yes, sir.
30, 10 goes to 33, remainder 0.
Yes,
The
sir.
next to be 40, 10 goes to 40, how many?
4 remainder 0.
Okay. Up to the next is 99. So the next is 100. 10 go to 100, how many times?
10 times.
10 remainder 0, right?
Zero.
And this 10 goes to 10, how many? 1 remainder 0, and this 0 repeated. So we write this 100. Is that correct?
Okay.
That's correct, right?
Yes, sir.
All right. This is because we are counting in a decimal base 10.
Hello, sir.
Yes.
Okay, so if I get it clearly, so it means like the whole world we understand, we come to an agreement that we are counting in base 10.
It's a conventional, it has a conventional counting process.
Okay, so it means that can change, like it can change, and we'll be counting in base 3, in base 4, and others.
You can count in any other base. Even there are bases that are bigger than base 10. When you look at your calculator, you have base 12 on your calculator.
Okay.
Yes, sir.
Okay,
Yeah.
we understand.
And you realize that the number 10 is not represented with the 10. It is the 12. That 12 goes to itself 1 remainder 0. That's what you see 10. I hope that is clear. Now,
Yes,
we
sir.
are going to count it base 5. Okay? And the base, no number should be seen which is equal to or greater than the base. So base 5, you have 1, 2, 3, 4. The next is 5, right?
Yes.
But remember, we are counting in base 5. How many times will 5 goes to itself?
1.
Remainder.
Remainder 0.
Okay. So the next will be 1 remainder 1, 1 remainder 2, 1 remainder 3, 1 remainder 4. The next will be 1 remainder 5.
Yes, sir.
1 remainder 5. But the 5 here is equal to the base.
Yes.
5 goes to 5. How many times?
1 remainder 0.
1 remainder 0. This 1 plus 1 will give you what? 2. So this whole to be 2 remainder 0. So 2 remainder 1, 2 remainder 2, 2 remainder 3, 2 remainder 4. The next will be 2 remainder 5.
2 remainder 5.
So you have 2 remainder 5. But the 5 will go into 5. 1. And that one becomes another set of 1. So this
Yes.
becomes 3 remainder
3
0.
remainder 0.
And the counting continues that way.
Okay, sir.
And if we count to 50, it means that 5 goes into 50 10 times remainder 0, and it's still going into 10.
Bro, someone.
I think 50 will be 100, isn't it?
Yes, sir.
Okay. All right. Any question? So if you are counting in decimal base will make you use of Boolean's numeral. Binary base. Binary base make you use of Boolean's numeral. Ruth, what do you know by binary base? Binary base is base 2, okay? Base 2. So that's 1. The next is 2, right? 2 goes into 2.
Sir.
How many times?
1 0.
1 0. The next is 1 1. The next will be 1 2. 2 goes here. You have
1 0.
1 remainder 0. So you have zeros. This plus this will give us 2. And there's a 2 here too. 2 goes into this to give you 1 remainder 0. So this will be 1 0 0. 1 0 1. 1 0 no. 1 0 2. So that will be 1 1 0 and so on. So the problem here is these are counting processes in decimal or other bases. But we are going to do addition, subtraction, multiplication in any other base other than decimal base. But we'll end it here. Any question? No question, right? All right.
Hello, sir.
Sir,
Please, can I suggest that when we meet face to face next week, please, can we go over like one example on each, like on the number base? Okay.
Your suggestion was rejected at Arava. The online lecture system is part of educational system. Okay.
Sir.
Yeah.
Looking at the examples in the handouts, where we have simplified the following additions in the given basis. So I just want to find out, is there a possibility where we'll have the numbers in different bases, but we'll be asked to make addition with them, simplify them?
Yes, that possibility is there. When designing a program to solve a real world problem, you need this kind of possibilities. You need to do that. And what you have to do is to make sure you can add in different bases, okay? You have a common base, you convert to a common base and do the addition.
Okay.
If it's got to subtraction, you convert to a common base and do subtraction. You cannot operate on numbers in different bases.
Okay.
Hello, sir.
Yes, sir.
Sir, please, that and that's still available.
The handout is lying down in my office and students refuse to buy after I spent money to print them.
So I need some, that's what I'm asking.
I have it. It's in my office.
Okay, sir.
If you want it now, come for it and bring the money.
Okay.
How do we locate office?
Face to face. That was next week.
The office is 218.
Come again, please.
You asking how can you locate my office?
Yes, please.
The office is 218. Class rep, please give me the list of all those who buy the handout.
Okay, sir. All right, sir. I'll do, sir.
Okay.
I'll do so.
Hello, sir.
Yes, sir.
Please, can there be any case where they wouldn't give you the base you have to convert to? But
If there's no basis to the number, it is by default base 10.
Okay, by default it is base 10.
Yeah, if there's no base specified, by default it's base 10.
Thank you, sir.
All right. So, thank you for coming.
Thank you, sir. Hello, sir.
Yes, sir. Please talk.
Please, one of our colleagues asked a question that in case you meet a question that the bases are different, how do you solve it? And you said you convert the base to one base. And I'm asking if, let's say, 125 plus maybe 155 base 3.
You cannot have a number you cannot have a digit in the number that to be equal or greater than
Yeah, please, that's my question is if we should two different base, how in which common base do we convert to?
That work is your choice to decide. but the life is easier if you can convert all of them to base 10.
Oh, okay.
It's easier and shorter. You know, let me tell you something. Designing a solution
Some
to
people's
a problem.
mics are on. Oh.
No, class is over. They can talk. Designing a solution to a problem. Anybody at all can write a program, okay? And the program can solve the same problem. But efficiency of the program is very key.
So you guys, the lecturer is still talking.
I hope you understand that.
Yes, sir.
Yeah. So somebody may write a program that will have to execute a number of steps. And somebody can simplify that within shorter steps. And it take its time complexity to be much lesser than any other one. That's the time it takes to execute to the end.
Okay.
So the decision will be yours. But to convert from one base to another base other than base 10, it definitely you have to go through convert it to base 10 and convert it back to another base.
Okay.
So you look at which one is the shortest possible route for you. Life is easier if you can identify the shortest possible route, the easiest way of solving a problem.
Okay, sir.
Okay.
Thank you.
You're welcome. Is that all?
Sir.
Hello, sir.
Yes, please.
Please, is there any way we can get the videos for the class, videos of the class?
I have not been reminded, so today's class has not been recorded. But the previous ones have been recorded, and
okay, so please can we have
the so it's there for you. It's just a matter of your class coming for it. That's all.
Okay, so we asked him, he says it has not been provided to him. That's right.
Well, the class wants me to come to his house and give it to him to give it to you.
I came there. I came there, and your assistant said your TA said you will send the link up now.
Class rep na video. Say bisa video yeah. Class rep they say oh yeah fan send me. Hello be bisa and also our class rep na was so bad. This wa ba hon ma hello this you or see or no the best send no say does he expect me to send it to bring it to him?
Michael, mute your mic. Mike, mute your mic.
No, I think he's explaining something. Okay. Michael.
I came to the office to take the video. Your TA
said that I should give him my number. He would send to me. I reminded him yesterday. No, that was 3 days now. He didn't send it. And the last Zoom meeting we have online, it was recorded by one of our colleagues. We have to post it online for them to view it. So
So
far,
you want
Yes.
us to upload it on LMS?
It's me, Jacob. So I still have it. I'm working on it to upload it. Yes, please.
even the last
But
time we remind you of it, right?
yes,
You mean you
please.
reminded me of
But
it?
The last time